Welcome to Skeleton Unlocked, where we explore how skeletal structure supports form and function. In this presentation, we'll look at bone types, microstructure, mechanics, growth, healing, and pathologies, tying visual diagrams to practical principles so you can see how bones are engineered for strength, movement, and lifelong adaptation. This slide compares long, flat, short, and irregular bones and highlights how shape predicts mechanical role. Long bones have cortical shells resisting bending. Flat bones act like protective sandwich structures for organs. Short bones form compact cuboidal units for force dissipation. And irregular bones, like vertebrae, combine a cancellous core with complex form to cushion axial loads. Here we focus on the osteon, the basic unit of compact bone. Concentric lamellae surround Haversian canals carrying vessels and nerves, while the lacuno-canalicular network houses osteocytes that sense fluid flow and strain, enabling nutrient delivery, mechanosensing, and remodeling that together optimize material properties in response to loading. Spongy bone is presented as a dynamic three-dimensional lattice. Trabeculi align along principal stress trajectories to maximize stiffness with minimal mass, leave space for marrow and hematopoiesis, and remodel rapidly in response to mechanical and metabolic signals, providing an efficient, adaptable internal architecture, unlike dense cortical bone. Bone is a composite material combining collagen fibrils with hydroxyapatite crystals and regulatory non-collagenous proteins. Collagen provides tensile toughness, mineral gives compression resistance, and proteins like osteocalcin regulate mineral deposition, producing a remarkable strength-to-weight ratio that outperforms many engineered materials while maintaining flexibility and toughness. This graphic breaks down the cellular players in remodeling. Osteoblasts build matrix, osteocytes act as mechanosensors coordinating activity, and osteoclasts resorb bone. Together, they balance calcium homeostasis and repair microdamage, so bones continuously adapt their structure through signaling and local remodeling to maintain strength and function. Joints combine cartilage, synovial fluid, ligaments, menisci, and optimize geometry to enable low friction motion and long-term durability. Cartilage provides a smooth, shock-absorbing surface. Synovial fluid lubricates and nourishes tissue, and ligaments guide motion and stabilize, all working together to distribute load and minimize wear over millions of cycles. Bones act as levers to convert muscle contractions into movement, with first-class and third-class lever examples showing trade-offs between force and speed. Most limbs use third-class levers to prioritize range and speed of motion, while lever arm geometry determines mechanical advantage and, ultimately, how muscle placement affects force transmission and movement efficiency. Endochondral ossification explains how long bones grow in length. Chondrocytes in the growth plate progress from resting to proliferating, hypertrophic and calcifying zones. Then blood vessels and osteoblasts invade to replace cartilage with bone, a process driven by hormones like growth hormone and IGF-1, until the epiphyseal plate closes and growth stops. Fracture healing recapitulates embryonic bone development in stages. An initial inflammatory hematoma is cleared. A soft callus forms with fiber cartilage and vascular ingrowth. Osteoblasts then mineralize the callus into hard-woven bone. And finally, lamellar remodeling restores organized, strong bone, illustrating how repair mirrors development through coordinated cellular activity. Common pathologies reveal how normal load-bearing functions can fail. Osteoporosis thins trabecules, increasing fracture risk. Osteogenesis imperfecta weakens collagen, causing brittle bones. Osteomalacia impairs mineralization, leading to deformed bone. And osteoarthritis degrades cartilage, producing joint pain and stiffness, each demonstrating the importance of structure for mechanical performance. Wolff's Law ties mechanical loading to bone optimization. Weight-bearing stimulates osteoblast activity and remodeling, producing thicker cortical shells and denser trabeculus in loaded regions. Practical recommendations include resistance training adequate calcium and vitamin D, and maximizing peak bone mass to enhance skeletal resilience and reduce long-term fracture risk.